Hi everyone, it's 1 Eastern Time sharp, and we are starting our webinar. Today we have Maria Riazantseva with her talk. Maria Riazantseva graduated with honor from the physics department of Moscow State University in 2003. Then in 2005, she obtained her PhD degree. At the moment, she is working at the Space Research Institute of the Russian Academy of Science as a senior researcher. Her research interests include experimental studies of the solar wind, development of space plasma instruments, processing and analysis of their measurements. The investigations of small-scale plasma fluctuations and properties of turbulence in the solar wind and magnetic sheath are in the focus of your current research. So please go ahead, and you have your 40 minutes before warning and 45 minutes before you.
Thank you, Gregory. The topic of my presentation is observation of small-scale plasma fluctuation in the solar wind. First of all, I want to speak about the main tasks of high resolution plasma measurements in the solar wind. Its thin structure of the interplanetary shocks. You can see here the high resolution plasma measurements and the detailed structure of IP shock fronts and some wave processes after this shock. The jet fin character of the solar wind. So in the solar wind, we can observe not only the fluctuation of ion flux value, but also of ion flux direction. Like as in shower, the solar wind has a structure of thin jets with different directions, and these jets can interact one to another. And the next is kinetic current sheets. It's a very popular topic now, so you can see here the measurements of a lot of current sheets and some simulation of it. And last but not least, it's the solar wind turbulence at ion kinetic scale. And actually, it includes all these fluctuation inside. So you can see here some simulation, and you can see some vorticities, small-scale structures, thin current sheets, wave processes inside. And all it can be seen inside the spectrum of turbulence. You can see it here. Fast plasma measurements in the solar wind have a great long history, and all began from 1973 by measurements of OGO5. It was measurements of ion flux up to 30.3 Hertz by Unchi. It was the first spectrum of turbulence. And the next was Kelnicker and the measurements of electron fluctuation at IC1 and 2 up to 5 Hertz. 10 years later, interval 1 measurements up to 1 Hertz, and 20 years later, cluster measurements up to 2.5 Hertz. And recent measurements, non-direct electron density measurements from spacecraft potential at Artemis mission, MMS mission up to 30 Hertz and for electron and 6 Hertz for protons. Parker Solar Probe up to 128 Hertz and Spectra R up to 32 Hertz. But practically all these measurements can observe solar wind turbulence at kinetic scales only in some examples, only in burst modes. So it's not systematic investigation. It's only with our mission, Spectra R, we can measure solar wind turbulence with high resolution measurements systematically. So I will be speak about Spectra R in more detail. And you can see here our instrument. It's the BMSV. It's experiment plasma F at spacecraft Spectra R. And you can see here also the comparison of Spectra R high resolution plasma measurements, the density and velocity in comparison with monitor of solar wind, 3-second time resolution, and you can see only several points at wind measurements, and a lot of points and a lot of detail fluctuation by Spectra R. So it was Spectra R was an astrophysical mission with highly elliptical orbit up to 63 F radius. And with long time service in the solar wind and with some crossing of ball shock and magnetic sheath. The operation time of mission was until August 2011 up to January 2019. And we have the possibility to measure ion flux vector all operation time with high time resolution of 41 millisecond, and I think half of operation time, all other solar wind parameters, density, velocity, temperature. It was a very good collaboration of Space Research Institute, Russia, and Charles University in Prague. And this collaboration is up today, and because we continue to work some solar wind experiments with high resolution solar wind experiments. Now it's the next the MSV for Lunar 26 mission, Russia Planet in 2024, and there are several other missions. What are the benefits of BMSV instrument? First of all, it's the possibility to investigate the kinetic part of turbulence spectrum. So here you can see the spectrum fluctuation of ion flux fluctuation in a larger range of scales. And the white part is the limit of systematic direct measurements before Spectra R. And the light blue part, it's the possibility of BMSV. So you can see that all kinetic scale is inside this blue part. So I need to say also that the ion flux fluctuation is, as a rule, it's the same as density fluctuation, as it was shown in Gebauer and the Pittler publication. So if I will show later some picture of ion flux, it's practically the same as density in most part of cases.
So could you clarify what is PSD flux? What is the abbreviation PSD?
Power spectral density. Power spectral density. So for Fourier spectra and power spectral density of Fourier spectra. Let's return to our science problem. So the phenomenon of turbulence. The people are interested in turbulence, I think, during last 5 centuries. And first was Leonardo da Vinci. And he created this term, turbulence, from Latin turba, a crowd of disordered people with an idea of allowing intimidation, each strolling around following a given direction. So you can see here also a very nice picture of Leonardo da Vinci with a lot of vorticities inside I think it's water. And the problem of turbulence in water was very actual for people during long time. You can see also the picture of Katsushika Hakusai, the great wave of Kanagawa. And it's not only the great wave. You can see here also a lot of vorticities inside its structure. And I think during a long time it was actual only for water turbulence or air turbulence, but at 20th century it became also actual for some plasma turbulence in laboratory plasma, as in tokamak. In astrophysical plasma object and also at the sun. And the solar wind is a nice laboratory of turbulence because space plasma is a collisionless turbulent medium with very high Reynolds number. And in solar wind, charged particles interact one to another only via electromagnetic forces, so electric and magnetic fields. And that's why it's a very interesting object, and it's strongly differed from water and from air turbulence. We need to say that most of plasma energization processes is expected to occur at kinetic scale, so it's scales of proton and electron radius and below. And the solar wind, it's nice possibility to look inside these kinetic processes and to answer a lot of questions of physics at these scales. In the solar wind, there are a great problem. It's non-adiabatic decay of proton temperature. You can see here a figure from Matthews et al. In 1999. The measurements of Voyager 2nd and the great difference of these measurements and the adiabatic prediction. And the turbulence is one of the most actual candidate to explain this non-adiabatic decay. What we also can to do in this fine laboratory, we can investigate some general processes of energy exchange between structure of different scales. We can also investigate some solar wind plasma heating and acceleration, and the proportion between the dissipation, the energy dissipation of different type of ions and electrons. And the next and very actual is the development of some correct models of plasma expansion from the sun to the earth and inside to the magnetosphere, because during a long time the most part of models were based on some magnetic hydrodynamic approach, and it's not good approach for some dynamic processes because there are a lot of interaction between the large structures and a lot of local processes, including kinetic scales too. So we need to take all this into account if we want to create some correct models. So the measurement is very good, but I think that a new brief to solar wind turbulence was given by appearance of some simulation model. So it's some model like Valerian Vlasov simulation by Valentini, hybrid flux of Maxwell model by Servideo, debris simulation by Karma Body, debris Maxwell model by Lincoln et al. And all these figures looks very beautiful, and I think that the most part of beautiful pictures of a solar wind turbulence is the result of such simulation, because the measurements results is often not very very effect. It looks like only the measurements of the curves or the spectra, but such two-dimensional or three-dimensional figures and construction is possible only with simulation models, and it's a very powerful tool. And I repeat, after appearing such models, the investigation of solar wind turbulence is very strongly increase in a number of papers and in interest into this area. So several main points about the turbulent cascade. So you can see here their measurement of ion flux at different time scales: 8 hours, 20 minutes, 40 seconds. And you can see high level of fluctuation on all scales. So if we look at small scales, we again will see a lot of small scales fluctuation. And each of these scales can correspond to the scale of turbulent cascade in the solar wind. So the first part of this cascade is a large plasma structure in the solar wind corona. So with slope -1. The next, it's named energy containing range. The next scale is inertial range. So it's the scale of energy transfer from energy containing scale to dissipation scale. And this corresponds time scales 10 minutes and hours. And the last panel corresponds to dissipation range, where the dissipation and heating take place. The next is the electron dissipation scale, but there are not a lot of information about this region. So what about the different the scales, the structure at different scales? So large scale structures is some solar origin structures, so coronal holes, coronal mass ejections, crustation and stream interaction regions, and some heliospheric current sheet, etc. The middle scale structures is the structure also of solar origin, but it's some remnants of magnetic structure of the photosphere, for example, as in this case, and also flux tubes, as in Brunner paper. And flux tubes mapped to scales of granule and supergranule at photosphere. So it's again the solar origin. And the last is alpha waves. So all these large scale and middle scale structures have the solar origin and is connected to the topology of the source region at the sun. And what about the small scale structures? Small scale structures have a local origin. They connected to the nonlinear dynamics of fluctuation. So, for example, it's some Alfvén vortex, as in a paper of Riazantseva et al. And, for example, some kinetic current sheets, as in a Rutina paper. And I need to say about the recent review of Khabarova Olga. I think that everybody in this community know her, and is concerned of this problem too. So small-scale structure is first of all vortices, waves, some sharp discontinuities and shocks, and of course current shifts, including kinetic scales also. So, and what is the proportion between the wave structure and some congruent structure? We can say that solar wind is always some mixed of including galvanic fluctuation, congruent and non-congruent structure, and all the structure are backed by the wind. In Bruno et al. Paper, he revealed that in fast solar wind, most part of fluctuation have galvanic character, and in slow solar wind, the fluctuation are not galvanic. At the same time, Borowski, in his investigation, study the difference, the proportion of the distribution, different type of fluctuation between the population of turbulent galvanic fluctuation and population of discontinuities. You can see here the core of distribution and the tail of the distribution. In his earlier papers, he sketched some flux tube structure, so some magnetic flux tube, and he say in this paper that the core of this distribution, it's the inner part of this flux tube. At the same time, the population of discontinuities, it's the walls, the borders of this flux tubes. And all this was discussed the inertial range of turbulence. But if we look at ion transition range in Line et al., we can see that congruent structure and non-congruent structure in some give near 80% and only 20% by waves. So the situation changed dramatically to kinetic scale. And what we can say about their view of the turbulence spectrum in the solar wind. So there are in traditional point of view, there are three slopes at this turbulence spectrum. The slope -1 in the energy containing scale determined by solar activity. At MHD scale, there are slope, Kolmogorov slope, -5 to 3. It's in case of strong turbulence and some incompressible galvanic fluctuation. It's typical for magnetic field and density fluctuation. And the slope -3 to 2 in case of weak turbulence. This case is typical for velocity fluctuation. And at this scale, at dissipation scale, at kinetic scale, we can see at traditional model slope -7 to 3 is a cessation of kinetic galvanic turbulence or ion cyclotron waves. And in some other model, the slope is steeper, -8 to 3. In case of kinetic galvanic turbulence, including several two-dimensional structure. And I need to say that this scale is strongly dependent on solar wind condition, and the situation, the model situation, is not very open. At the same time, I need to say that all this approach, that analysis in spacecraft frequency frame, It's possible only because the tailored hypothesis is working in the SolarWind. So we can point that the fluctuation observed at a single point in space can be interpreted as some special variation, and this special structure they pass with some bulk velocity by the spacecraft, and we observe this fluctuation as some time rose, but nature is special fluctuation. It works for most part of spectrum, but it's related for Whistler rays. But happily, the Whistler rays are not very significant in the SolarWind. But in case of foreshock or magnetic sheaths, the situation is more dramatical. So at the previous slide, I have said that the model is predicted -7 to 3 or -8 to 3, and mean spectrum is traditionally very near to this prediction, -8 to 3. So you can see here magnetic field fluctuation by Kelly-Stowe, magnetic field fluctuation by cluster, magnetic field and electron density fluctuation at the same figure by Artemis, and our ion flux and density fluctuation at spectra R. And in these cases, the slopes is very close each other. But I need to say that this situation is not absolutely typical. And the next interesting point is the break point between the inertial range and dissipation range. And in literature, there are discussed a lot of different plasma scales. First, it's ion cyclotron frequency for in traditional model of turbulence, and the scale of ion thermal Gera radius and the frequency connected with this scale by Chekhachukin et al. Its scale of transition of galvanic turbulence to the kinetic galvanic turbulence. The next scale is the inertial length. It's typical for if in case if turbulence has a large parallel component. So in case of current sheaths, for example. And also in some papers discuss some combined scales. And the next figures, they show the experimental study of the position of the break. And the position of the break, the difficulty is that these two scales is very close to each other for most part of measurements, because the beta is near the 1. And we need to select only very low or very high beta value, as in this paper, to separate the scaling. And in this paper by Chen was shown that for small beta, the ion inertial length scaling is good well, and for high beta, opposite, the ion thermal Gera radius is work. But if we look at large statistics by our spectra R measurements by Shafrankova et al., we can see that the situation is more complicated, and there are the very broad dispersion of these dependencies. And there are a lot of different interesting features inside the spectrum. So for example, we can see in density spectra some plateau. It's typical only for density spectra, not for magnetic field. And it was observed also at very early measurements in 1973. And it was also predicted by Chandran et al. As some superposition of galvanic turbulence and kinetic galvanic turbulence. So the dashed line is kinetic galvanic turbulence, the straight line is the galvanic turbulence. And you can see that in case of low beta plasma parameters and the different curves is the level of fluctuation. So the lowest fluctuation, highest fluctuation. So the situation of this plateau can see very strongly for case of small beta parameter. And the next interesting problem is their spectral steepening, the anomaly spectral steepening. It was can be observed for high-speed streams in the solar wind, for example, downstream the interplanetary shocks and in magnetic clouds. In Brun et al., he suggested that these dependencies can be related by some dissipative mechanism, but in other paper is discussed that it's the results the co-collision processes, so the kinetic galvanic waves can move with different velocity, and this co-collision can be result in anomalous spectrum. So in solar wind, in our measurement, we see that all these type of spectra can be seen in complex. So with traditional model situation is not very often, and there are a lot of other situations in a different type of solar wind. And here there are a movie with dynamic of spectrum of turbulent fluctuation, and you can see it's begin. So the small spectral bump can born and grow, and after all spectra become more intensive, and so the different spectra types can be observed practically in the same time, so one next to another. And now we will move to our investigation. Our last investigation is concerned to this anomalous steepening. So it's typical for some Cartesian interaction region or some stream interaction region. You can see here the compression of the turbulent spectrum. Blue lines is slow solar wind, red lines is stream interaction or Cartesian interaction region, and you can see that the spectra in interaction region become more powerful and with very steep minus 3.7, minus 3.1 at the kinetic scale. So in MHD scale, the model prediction work rather well, but at kinetic scale, the prediction of whole model is in a better agreement. So we collect a lot of such spectra, and you can see the distribution of spectral slope. So the dashed line show -5 to 3 for MHD scale, So the distribution in all solar wind types is near the theoretical prediction. But if we compare the kinetic scale slope, we can see that prediction -7 to 3, -8 to 3, and the maximum of distribution of most type of spectra, exceptionally in the stream interaction region and Cartesian interaction region, is strongly different from this model prediction. And also, if we compare the position of the break with discussed earlier plasma scales with frequency connected to proton gyroradius or ion inertial length. And we also compare some statistics. So it's the distribution of this proportion for stream interaction and Cartesian interaction region and for other solar wind types. And you can see the same situation for the proportion of the break frequency to ion inertial length. And you can see that the maximum near 1 is typical for stream and interaction region and not typical for other solar wind types. And in case of the second proportion, only slow solar wind observe the maximum near 1. So the break frequency is related in sheath and zero with the radius of the proton, and in steady slow solar wind with inertial length. So the next point is the intermittence in the solar wind. So it's a very interesting problem because if we look at any kind of measurements, so for example, ion flux measurements and interval and wind, you can see that the inhomogeneous of these sharp borders. So some quiet periods alternate with activity region. And it's mean that some intermittency is observed inside solar wind. So you can see that we can see it all set models, and if we do some sketch, we can imagine that some of the eddies with construction disappeared at one moment. And as a result, you can see such picture. And we need to take into account that a lot of models in solar wind was created for some trivial self-simulatory situation. So in this case, then the eddies of the small scales repeat the form and properties of large eddies. So it's the situation as in Roman broccoli. You can see that if we look at one part of this figure, the same small so the same structure can be seen at smaller scales. So self-similar object is similar to a part of itself. And in solar wind, the situation is dramatically differ from this trivial self-similarity. And both, as you can see, that the small scale fluctuation do not repeat large scale fluctuation. And in terms of intermittency, possibly we can find extended self-similarity, but we need to check it. So what about measurements? for intermittency is typical non-Gaussian statistic. So statistical properties of the signal strongly depend on the position of the selecting window. So
Maria, you have
okay.
5 more minutes.
Okay.
5 more minutes.
Okay. So in different observation, we can see the situation that on large scale we see some Gaussian statistic, and on small scales we see non-Gaussian statistic and flatter tail in Helios 2 measurements, in cluster measurements, and also at spectral R measurements. So we can use some higher order statistics. First of all, flatness, and it's a fourth order moment. And it was used, for example, by Alexandrova and in our papers. In these papers, the flatness grow very significantly at kinetic scale. So the intermittency is really exists in the solar wind. If we look at high order statistics, the situation is more complicated. I have no time for details, but the dependence, the high order statistics are absolutely non-linear. But we can find the dependence of the structure function of Carter order and structure function of some fixed order, for example, on third order. And if we see some linear dependence, we can speak about extended self-similarity. And in solar wind, by our measurements, it's absolutely this situation. So we can prove that it's extended self-similarity. And we can use some log Poisson model of intermittent turbulence, which can describe better the such intermittent flow, and to use different approximation, different parameterization. And in our results, we have shown, it's our results, Kolmogorov and log Poisson models, that the better description can be for the log Poisson models with filament structure. So like in spaghetti flux model by Bruna. And the last, I think, two figures, it's about turbulent and magnetic sheet, very briefly, that all discuss that the solar wind is turbulent, but the magnetic sheet is more turbulent. You can see here the experimental measurements, and the level of fluctuation grow in four-shock and in magnetic sheet region. It's a really problem, but there are some last Gilbert models that can predict such situation. So we hope that the situation can be changed in next several years. But why it's very important? Because the previous MHD model and magnetic sheet do not describe the turbulence. And you can see here the comparison of models, Sprighter model and real measurements, and the difference is very strong. So we need, and at the same time, the magnetic sheets include solar wind turbulence and add some fluctuation born inside magnetic sheets. So it's very complicated to review what's will be the processes in magnetic sheets, and how does the turbulence evolve behind the bow shock. And my last figure is some brief review of my PhD student results, Rahmanova et al. And she investigated the plasma turbulence processes inside magnetic sheets. and she has shown that she investigated turbulence spectrum, and she has shown that directly behind the bow shock, spectrum become flatter at MHD scales and steeper at kinetic scales, and spectra return to model view during its moving to magnetopause. As a conclusion, we can say that the compression fluctuation suppressed behind by bow shock and develop again with further plasma motion. I understand that it's a very brief results and see more in the review Rachmanova et al. In Frontiers Space and Astrophysics in this year. I will move to summary remarks. The classical spectra of solar wind turbulence can be observed only in some pristine, not disturbed solar wind. It's the situation of freely developing turbulence. At the same time, the situation of some stream interaction and the CR gradation interaction region is very interesting because the boundaries between this structure is limit the turbulence development. So the model can't work in this region, and we see the situation of very steep spectra at kinetic scales, the character of dissipation can really change if we cross from slow solar wind to some high stream speed region due to some velocity shift. The position of the break is also strongly affected by the solar wind types, and it's usually controlled by the scale of proton radius for stream interaction region and gradation interaction region. And it is controlled by ion inertial length in the steady slow solar wind. The turbulence spectra can be significantly modified at the bow shock and return to model view during plasma moving to magnetopause. And the last, it's that the high level of intermittency is very typical for solar wind. And we can describe a statistic of plasma fluctuation with the solar wind with some log Poisson models with dominant contribution on filament-like dissipation fraction. So I think it's all this moment, and I wait for a question. I'm sorry that I take a lot of time.
Thanks, Maria. Can you hear me?
Yes.
Okay, so thank you, Resh. It was very interesting. I think there is a lot to be digested. So we are now open for discussion, questions and discussion. So please raise your hand and then unmute your microphone and ask question or make a comment. So right now I do not see any raised hand yet or unmuted microphone. Are there any questions?
Hello, it is Irina Kitiashvili. I have a question. Okay, so first, thank you very much for very interesting educational, for me, educational presentation. I'm not working in solar wind. And my question is about intermittency, what you see in spectra. Do you have any physical explanation for this? You showed some breaks in turbulent spectra and discussed about it, and I just wondering if any physical explanation of this.
So the physical explanation of intermittency as a whole? So what about...
You showed some turbulent spectra of solar wind, and
yes.
show like some I believe, yeah.
You want to know about the relation of turbulence spectra and intermittency? Yeah. So if I understand the question, so the intermittency mean that there are I have discussed that there are the borders of large-scale structures, but at the same time there are the borders of small-scale structure, and it is also influence on solar wind turbulence. So really the idea that the turbulence can freely develop in space doesn't work at all. So all models with this assumption can't be used, and we need to use some statistical models which take into account this intermittent structure and non-homogeneities of the structures in the solar wind. So if you can see at this in this figure that if in dissipation scale, in kinetic scale, we see that the spectra becomes steeper, and at the same time there are highest the level of intermittency increase. So the physical sense is that there are a lot of small-scale structure which is shown by the flatness increasing, and this structure is a good for dissipation processes. So the dissipation work very intensive on this amount of local structures. So.
Thank you.
Irina, is that fine?
Yes, I have one more question, but probably
Go ahead.
somebody.
Go ahead.
Yeah, it is again maybe a simple question for you. So, can you little bit discuss how change properties of turbulent spectra with solar cycle?
The solar cycle, I think it's very difficult because it's. I have discussed that the turbulent properties is very affected by some borders of large-scale structure. So in solar maximum, we have more large-scale structures as coronal mass ejection, and of course we have a lot of situation with anomal spectrum steepening at the kinetic scale or something like this. But if we do not look only on a large-scale structure, if we look only on slow solar wind, I think that slow solar wind, the turbulence in slow solar wind will have no change here. So all change in cycle will depend on the appearance of large-scale structures, I think. But I don't know any investigation because it needs a very long time measurements during several decades, and on all these results, as I have shown, it's the high time resolution plasma measurements. It's also during the, I think, last several years, so like spectra are MMS, Parker solar probe, and we can't investigate the influence of solar cycle yet.
Yeah, thank you. Thanks a lot.
Thank you. Thank you for the
Okay,
question.
more questions or comments? Maria, I've been wondering, could you just reiterate, you mentioned and discussed this, just differences between like key properties of turbulence in high beta and low beta cases. Could you again summarize? Just I believe I missed something there.
One moment. Yes, it was the result in previous paper. The most difference is of the position of the brake. In case of the small beta, the brake is related to the ion inertial length, and in case of the large beta, the position of the brake between MHD and kinetic field is related to the ion thermal radius. It means that the different type of dissipation processes is dominate for different beta. But really, I have no put my figure. It's not easy to find such examples with such separating scales. In most of cases, the scaling is very close one to another, and we need to find something other because the position of the brake sometimes correspond to one scale, some to another, and if these scales are close, the difference can be very difficult to find. But in our analysis, we go by other way. We try to compare the brake frequency and the scaling in each spectra, and to determine this proportion. And with this analysis, we found that the situation in the stream interaction region is correspond that the scaling is near to ion radius frequency, and you need to take into account that the beta parameter is this case is near 0.5, and in situation of low beta in magnetic cloud, there are no proportion. This proportion is lower than 1 for this case. So the situation is not so easy. I conclude that as Chen discussed, it shows the nearest scaling, but it can't work statistically. We can look only in each case, in each spectra, what scale is working at this spectra and why. And we concluded that the type of solar wind is more important sometimes than the value of beta in this period. So I'm sorry for so difficult explanation.
Yeah, I guess very useful. So thank you very much. So, do we have any maybe last or almost last question or comment? Yeah, I don't see any raised hand or unmuted microphone. So let me thank our speaker again. So thank you, Maria, for your talk. And
thank you for the invitation.
Please, yeah, please, people, come again on the 3rd Friday of September for our next event. So thank you very much and see you next time.
Thank you. Bye.